August 1944. Along the southern coast of England, heavy anti-aircraft guns slowly turned on their mounts. Following the rhythm of a new radar system the Germans believed could not work with such precision in real combat. Across the Channel, German observation posts sent back reports filled with numbers that contradicted everything their engineers thought they understood. V-1 flying bombs moved steadily toward England, yet many of them erupted in midair as if struck by an invisible calculation. No fighters were chasing them. No barrage balloons were cutting their wings. The explosions appeared around them with uncanny accuracy, as if the British guns knew the exact moment each missile crossed a hidden line in the sky. At 6:15 on August 28th, a morning report carried a number that forced every officer to stop and read it twice. 82% destroyed in a single day. A number that tore through every ballistic principle taught in German technical academies. No one could explain how shells were bursting so close to the V-1s without scoring direct hits. No one understood how the missiles were being knocked out of the air before reaching land. And while German scientists struggled with equations that no longer worked, a small American device, no larger than a man's hand, was rewriting the rules of warfare above the Channel. A technology guarded with the same secrecy as the atomic bomb, hidden inside every shell fired toward the approaching V-1s. That night, London survived because thousands of tiny explosions formed a barrier no one could see. For the Germans watching from across the water, the reason remained a mystery. In the final weeks of August 1944, the narrow stretch of water between France and England carried the low, uneven pulse of the V-1 engine. The sound was unmistakable, a rough, mechanical cough, cycling at a rhythm that felt unstable, almost exhausted. Londoners had learned to recognize it instantly. When the pulse stopped, the silence signaled the final dive, in the last seconds before impact. For London, a city that had endured the Blitz 4 years earlier, the V-1 was an enemy of a different kind. It issued no long approach from high altitude, no swarm of bombers cutting lines across the sky. It came as a single, blunt delivery of explosive force, fast, direct, and indifferent. When it struck, it carved horizontal destruction through neighborhoods, collapsing rows of houses in seconds. But the greatest confusion did not unfold over London's streets. It occurred across the Channel, inside German observation posts positioned along the coast of occupied France. Their duty was to watch each V-1 as it skimmed over the sea toward England, to track its flight until distance made it too faint to see. On the morning of August 28th, a routine report was delivered to a German officer monitoring the weapon's progress. He read the number, folded the paper, reopened it, and read it again. 82% destroyed in a single day. There were no fighter intercepts, no balloons cutting wings, no reports of sabotage. The V-1 simply exploded in the air at distances that made no sense. German observers wrote that the British shells were detonating near the missiles, rather than striking them directly. The explosions seemed to appear at precise intervals, forming invisible rings around the V-1s before tearing them apart. To the German engineers who had designed the weapon, this behavior contradicted every principle of anti-aircraft fire in existence. Nothing in their textbooks explained it. Nothing in their experiments predicted it. Nothing in their intelligence briefings prepared them for it. And yet it was happening, dozens of times per night. What they did not know, what no German scientist had any way to imagine, was that a secret American device, small enough to fit inside a single shell, was rewriting the logic of air defense while remaining entirely hidden from them. To understand why the number 82% struck German command with such force, it is necessary to return to the logic that shaped the V-1 program from the beginning. By 1943, Germany faced a strategic crisis. The Luftwaffe had failed to break Britain's defenses during the Blitz. The loss of air superiority made manned bombing missions increasingly expensive. Hitler needed a weapon that could reach Britain without risking pilots, aircraft, or fuel. The V-1 was engineered as that answer. Its specifications reflected a simple concept of mass production and minimal complexity. Total weight, roughly 2,000 kilograms. Propulsion, Argus. As 109-014 pulse jet. Cruise speed, 640 to 650 kilometers per hour. Range, 240 kilometers. Warhead, 850 kilograms of amytal. Guidance, gyroscope-based control with a mechanical timer. The V-1 was a crude machine, but it matched the strategic needs of a Germany stretched across the Eastern Front and under relentless Allied bombing. More importantly, the German technical community believed the V-1 had a natural immunity to anti-aircraft fire. Why? Because in the early 1940s, radar could not compute firing solutions automatically. Everything depended on manual interpretation. Time-fused shells needed perfect calculations. A single mistake, speed, angle, altitude, meant an empty explosion in the sky. The target was small and extremely fast. Hitting a V-1 directly was like firing at a steel barrel, flying at the speed of a modern airliner. German analysts calculated a probability so low, it became doctrine: one successful hit for every 10,000 shells fired. The V-1 by design exploited this weakness. It flew straight, it flew fast, and it gave anti-aircraft guns almost no time to react. To the German high command, the weapon was the perfect combination of simplicity and strategic effect. A single V-1 cost a fraction of a bomber mission and carried no human risk. The numbers suggested London could be overwhelmed, and for a short time, the Germans believed exactly that. On June 13, 1944, 1 week after Allied troops landed in Normandy, the first V-1 struck London. It slammed into Grove Road in Bow, shattering homes, killing 6, injuring dozens, and leaving 200 homeless. It was the first blow in a long series of attacks meant to drain British morale and force the government into defensive focus. The pulse jet's uneven roar became a part of daily life. Families paused whenever the sound crossed overhead. Children froze when the engine sputtered. Adults counted seconds between silence and explosion, waiting to hear whether the bomb had landed near them or somewhere else. V-1 attacks did not produce the rolling waves of destruction seen in the Blitz. They created a kind of psychological compression, sudden impact, sudden violence, sudden grief. Meanwhile, the Germans believed that even a modest success rate would devastate London. General Walter Dornberger calculated that a mere 25% of V-1s reaching the city would drop more explosive tonnage than the Blitz of 1940-41, and nearly 5,000 were launched in the first 2 months. But while the weapon terrified civilians, it set in motion a response that unfolded with a speed the Germans had not prepared for. Within days, Britain recognized that stopping the V-1 required a new strategy. Fighters could intercept some of them. Balloons could force others to break course. But the real opportunity lay in the predictable line every V-1 had to follow. The British plan rested on 3 pillars. Pillar 1, bring your CR-584 radar to the front. The SCR-584 radar, provided by the United States, was not simply a detection tool. It could automatically track moving targets, calculate speed, direction, and altitude. Feed this data directly into the M9 fire control computer. This eliminated the guesswork that had crippled time-fused firing. Now anti-aircraft guns could receive precise, continuous updates. Pillar 2, move all heavy guns to the coast. This became the foundation of the diver belt, a network of heavy guns placed along England's southern shore. The logic was clear. All V-1s had to cross this line. Guns could fire freely without endangering Londoners. Unexploded shells would fall into the sea, preventing German recovery. The coast became a kill zone stretching miles. Pillar 3, deploy a secret device without telling the gun crews. Gunners received crates of ammunition, sealed in wood, stamped with special markings and accounted for individually. They were ordered not to open them, not to question them, and not to examine the fuses. Inside each shell was the technology the Germans believed impossible. The proximity fuse, a miniature radio transmitter receiver system that allowed a shell to detonate when it approached a target. Gun crews had no idea they were firing a weapon protected under secrecy as strict as the Manhattan Project. They only knew the shells worked. During June, the interception rate climbed modestly, 10%, then 24%. This was higher than German expectations, but still within conceivable limits. Then July arrived. German observation posts began recording patterns that made no sense. V-1s flying normally suddenly veered off course after nearby explosions. Fewer British shells were needed for each downed V-1. Explosions occurred at distances that should not have damaged the missile. One report noted, explosions appear to occur in stable clusters near the target, not on the target. Something had changed. German analysts assumed radar or training explained it. Their assumptions shielded them from recognizing the truth. At 6:15 on August 28th, a report reached Oberst Max Wachtel, commander of the V-1 campaign. 78 V-1s launched, 64 destroyed, 14 reached land, 82% interception. All mission logs agreed. All flight tests confirmed normal V-1 performance. All sabotage checks came back empty. The V-1s worked. The British defenses worked better. Wachtel examined the fall points on a coastal map. Almost all V-1s died within the same narrow band, a signature of precise, consistent anti-aircraft fire. The German chain of command could not accept that a revolutionary weapon had entered the battlefield without their intelligence network detecting it. Their conclusion, though wrong, revealed their mindset. The British have improved radar and timing systems beyond our predictions. They did not consider an electronic fuse because they believed it was impossible. Their disbelief became their defeat. Throughout the war, German engineers attempted to build proximity fuses. More than 30 designs failed. Everyone broke under the force of being fired from a gun. The obstacles were fundamental. 1. Vacuum tubes shattered under 20,000 G. No German material survived this. The United States solved it by creating reinforced miniature tubes from hearing aid designs. 2. Batteries could not activate at the moment of firing. German batteries degraded over time or failed under stress. American engineers invented a glass ampule battery activated by shock. 3. Germany could not mass-produce microcomponents. Factories were bombed, resources were scarce, and forced labor reduced precision. American factories produced 40,000 proximity fuses per day, 400,000 miniature tubes per day, 22 million fuse units by war's end. Germany's industrial capacity was not merely smaller, it was incomparable. Germany invested in expert craftsmanship and advanced prototypes, rockets, jets, guided weapons, but their output remained limited. The United States invested in scalable engineering, cross-institution cooperation, industrial specialization, the ability to turn theory into mass production. The proximity fuse was not elegant in the German sense. It was practical, it was repeatable, it was everywhere. When combined with radar and automatic fire control, it created a defensive system Germany could neither detect nor counter. The validity of the proximity fuse depended on secrecy. Britain took extraordinary steps. 1. All heavy guns moved to the coast. Unexploded rounds would sink beyond German reach. 2. Strict accounting. Every shell tracked, every casing recovered, every dud inspected and sealed. 3. Limited exposure on land. Ground forces in Europe were denied access to the fuse until December 1944 to prevent capture. The secrecy was absolute. The Germans never recovered a single intact unit during the V-1 campaign. By early September 1944, the V-1 campaign had become a statistical disaster. Interception rates too high. No captured evidence. No technical explanation. German engineers submitted reports filled with educated guesses, maybe improved radar, maybe better timing, maybe British luck. None of these theories accounted for the actual performance. Without data, the Germans could not solve the problem. Without imagination, they could not even articulate the question. The V-1 campaign ended not because the missile was flawed, but because Germany could not understand what it was up against. In June 1944, American, British, and Canadian troops were fighting through the bocage of Normandy, struggling for every hedgerow. The world's attention was fixed on that brutal ground campaign. Yet at the same time, another battlefield was forming, one without trenches, tanks, or infantry. It stretched across the sky above the English Channel. It became a battlefield where the Royal Artillery faced Germany's V-1 flying bombs. A battle measured in seconds, not in miles. After June 13th, Londoners heard the uneven buzz of the pulse jet every night. while the gun crews of the anti-aircraft command handled wooden crates stamped with special markings. Inside those crates was the most advanced fuse in the world, yet the men handling them were forbidden to know what they were firing. They simply followed orders. They fired. And their shells worked with a precision they could not explain. At that moment, without realizing it, Britain was entering the most important technological turning point of the campaign. Before the proximity fuse appeared, Britain's anti-V-1 defense consisted of 3 layers: fighter aircraft such as the Spitfire, Tempest, and Mustang; balloon barrages deployed to disrupt low-flying V-1s; anti-aircraft guns scattered across southern England. Each element contributed something, but none could deliver the results needed to protect London. The decision that changed everything: move the guns to the coast. Anti-aircraft guns positioned across London had limited firing arcs and posed a danger to the city if their shells detonated too early or fell unexploded. But along the coast, the situation was different. V-1s had to cross that line. Guns had a clear view. Radar operated without obstruction. Dud rounds fell safely into the sea. This became the origin of the diver belt, a concentrated coastal gun barrier. The second step: deploy SCR-584 radar in full operational capacity. SCR-584 was not a conventional early warning radar. It was a precision tracking system capable of locking onto fast-moving objects and feeding data into the M9 predictor computer. The result was a unified defensive machine. Radar tracked. The M9 computed. Guns obeyed. The proximity fuse completed the kill. No part of the system needed guesswork. The third step: introduce the proximity fuse without telling the men who used it. No explanations, no technical briefings, just ammunition crates sealed under strict accounting. Britain had just built the world's first integrated automated air defense network, and Germany had no idea it existed. By mid-July, the first patterns emerged. A gun crew near Sussex reported that after firing 8 shells at a V-1, 7 detonated in a clean arc around the missile. A few seconds later, the V-1 fell apart mid-flight. One gunner wrote in his diary, "The shell didn't hit it. It just burst near it, and the bomb dropped like something had snapped inside." Gunners did not know the fuse sensed distance. They did not know it emitted radio waves. They did not know the fuse armed itself in flight. All they knew was that for the first time, V-1s were falling with remarkable consistency. After the first 10 days of full field deployment in July, interception climbed to nearly 50%. Ammunition expenditure dropped drastically. The pattern of early kills appeared each night. These results climbed faster than any British commander expected. The stage was set for the turning point. General Frederick Pyle, head of Anti-Aircraft Command, received a report covering the dates: July 22nd to 30, 1944. It detailed 2,000 proximity-fused rounds fired, over 250 V-1s destroyed, roughly 8 shells per confirmed kill. The number contradicted every ballistic model the Germans trusted. It also confirmed something Britain had suspected: the proximity fuse needed full deployment. Once Pyle approved it, diver belt transformed into a lethal wall of automatic fire. The Germans still believed their calculations were correct, but they were fighting equations from 1940 while standing inside a war that had already entered 1944. On August 3, 1944, inside a converted building near Marquise, engineers and officers gathered for an emergency briefing. Maps showed clusters of V-1 crash sites forming a narrow strip just offshore. A technical officer stepped forward and said, "The British shells are not hitting the missile. They are detonating near it." To the engineering staff, this was impossible. The burst radius of anti-aircraft shells was too small. The time fuse was too imprecise. The odds of near misses forming consistent patterns were infinitesimal. Yet the data was clear. Wachtel refused to accept any theory outside known science. He ordered checks at saboteurs, none found. Mechanical failures, none detected. Timing errors, none recorded. He concluded incorrectly that British radar had improved significantly. His analysis reflected a deeper reality. German science believed it had reached the limits of what was physically possible. Anything beyond those limits was dismissed. This belief became their cage. From August 24th to August 31st, the numbers shifted dramatically. August 26th, 67%. August 27th, 71%. August 28th, 82%. The air defense network reached peak effectiveness. Why this sudden leap? Because for the first time, the diver belt was fully manned and fully aligned. SCR-584 had uninterrupted target acquisition across the entire coast. The proximity fuse reached maximum density and ammunition supply. Gun crews had refined firing routines to near-mechanical consistency. The V-1's straight-line flight made it the ideal target for automated fire control. August 28th was not an anomaly. It was the logical outcome of systems working together: human, mechanical, electronic, industrial. For the Germans, the result was staggering. For Britain, it was the day the tide turned beyond reversal. By early September, 9,521 V-1s had been launched. 2,515 reached London, but most were stopped near the coast. The campaign had lost its strategic value. General Pyle later wrote, "Without proximity fuses, casualties would have been 4 or 5 times higher." On the German side, there was a growing recognition. The V-1 had been outrun by the pace of Allied technology. This led to the final decision. The collapse of the V-1 campaign represented more than the failure of a single weapon. It revealed a shift in the nature of modern warfare. 1. Industrial capability surpassed theoretical brilliance. German engineers had skill. Allied factories had scale. 2. Automated systems replaced manual calculations. SCR-584 and the M9 computer eliminated human error. Third, multiplicative technologies reshaped the battlefield. A simple shell with a small radio circuit multiplied the effectiveness of every gun on the line. The turning point was not a dramatic battle. It was an alignment of engineering, production, logistics, battlefield deployment. The Germans never saw this alignment because it did not resemble their idea of warfare. The fundamental shift happened when gunners realized they did not need a direct hit anymore. Once they fired within the correct bracket of data from the M9 predictor, the fuse handled the rest. Their job became a race of speed, rhythm, and discipline, not precision. A gunner in battery ZS/5 wrote on August 29th, "We fired as usual, but the bombs fell like they had been struck. We didn't feel as if we were doing anything special." That sense of routine masked the reality the war had just tilted. The turning point was not loud. It was a quiet shift inside the firing rhythm of the coastal guns. A moment when the battlefield began to obey a new set of rules. In the final week of August 1944, the rhythm of war around London shifted into something unnatural. Explosions echoed across the coastline in irregular intervals, far, near, then far again. Residents counted each one with the quiet precision that fear teaches over time. The city had lived under threat for years, but this new phase was different. The V-1s were still coming, yet many never reached the capital. The true pressure did not fall on London's streets. It settled along the southern coast, where the Royal Artillery manned the diver belt. There, the summer sun heated the steel of the 3.7-inch guns until crews poured water over the barrels. Radar hummed, plotting targets without pause. Oil, sweat, gunpowder, and metal created a smell that clung to uniforms long after each shift ended. This was not the clean, distant science of missile interception. This was the physical, grinding reality beneath it. The proximity fuse worked in the air, but hell unfolded on the ground. A typical coastal battery had between 8 and 12 men, a radar assistant, 3 loaders, a gun layer adjusting elevation, a trainer handling traverse, a predictor operator, a battery commander. All of them were given strict orders. Fire what you are given. Do not question the ammunition. Do not open a fuse. Do not inspect one. Every proximity-fused round arrived in sealed containers marked for special accounting. Shells were counted in and counted out. Crews followed procedures they did not understand. The secrecy added pressure, a pressure that grew heavier each day as the V-1 campaign intensified. In the diary of Gunner Arthur Bell from the 12th HAA Battery, we saw the shells burst closer to the bomb than anything we had fired before. We didn't know why. Something was different, but we were not allowed to ask. They did not know their shells carried miniature radio transmitters. They did not know the Fuze sensed proximity. They did not know their guns were now part of the most advanced air defense system in the world. The shells worked, and the men were told that was all they needed to know. The diver belt was never quiet. SCR-584 radar continuously rotated, scanning the sky. Every detection, every faint blip from across the channel, triggered a sequence that transformed the coastal batteries into machines of pure timing. A typical night engagement followed a pattern. 0014. Radar picks up a V-1. Distance, 25 to 30 kilometers. Altitude, 600 to 800 meters. 0015. Gun crews stand by. No shouts, only the clipped confirmations of men who had repeated the drill hundreds of times. 0016. Ammunition arrives from the ready racks. The barrels glow faintly in the dark. Water hisses on steel. 001620. First volley fires. The guns roar as shells arc into the night. 001622. Second volley. The crews load without hesitation, each motion a practice part of a brutal choreography. 001626. V-1 erupts in midair. A flash, a brief cloud. Fragments tumble into the channel. Then silence. No celebration, no relief. Ops room reports. Target destroyed. Prepare for next. The radar turns again. Hell resets. The proximity fuse transformed the battlefield by eliminating the need for a direct hit. British analysis later outlined its impact. 1. Consistent near-burst patterns. Shells detonated within lethal range, even at high closure speeds. 2. Load reduction on gun crews. They no longer adjusted fuse timing manually. Their job was rhythm, not precision. 3rd, radio reflection, logic. The fuse emitted a signal. When the reflected wave grew strong enough, the thyrotron fired the detonator. 4. Weather immunity. Fog, rain, cloud, low light. None of it mattered. What mattered was metal mass near the shell. The fuse reacted to that alone. To Germany, this defied physics. To Britain, it was the new standard. Across the channel, German officers in coastal watch stations recorded strange reports. From a tap, one observer wrote, "Explosions occur not on the missile, but around it at stable intervals. British timing appears unnaturally precise." Another report stated, "The V-1 remains intact after some bursts, then suddenly breaks apart. Pattern resembles controlled detonation." They had no concept of a fuse that sensed proximity. They assumed improved radar, higher discipline, lucky timing. They did not consider a new kind of fuse because their own scientists had declared it impossible. Ignorance became part of the battlefield, and it cost them. While most V-1s were destroyed at sea, the ones that slipped through still carried their full payload. When they hit, they tore open neighborhoods with horizontal blasts that collapsed entire rows of houses. Areas severely affected in August included Camden, Chelsea, Brent, Lewisham, Fulham. The sound of the pulse jet became a signal learned from experience. A survivor wrote, "The engine cut out. Everyone froze. Then the ground hit us like a hammer." Even with the diver belt working at peak efficiency, London lived in a shadow where every silence could mark the next strike. This was a second hell, different from the one the gunners faced, but no less real. Inside the coastal gun sites, urgency intensified as the missiles approached land. Radar operators shouted distances. Gun crews accelerated. Nerves tightened. The V-1 typically covered the last kilometers in seconds. If crews missed their window, the bomb reached London. This created a psychological duel, the V-1 racing inland, crews racing to stop it. A delay of 3 seconds could mean dozens of civilian casualties. One gun commander said, "You felt the city behind you. If the bomb passed, you knew exactly where it was going." Every detonation above the channel meant lives saved inland. Every failure meant the opposite. Not all V-1s exploded when struck. Many lost stability after fragment damage. Wings clipped, fins twisted, gyroscopes cracked, engine vibrated out of sync. These bombs spiraled downward, falling into mudflats, shallow waters, or farmland before detonating, or failing to detonate at all. German intelligence noticed this too. Some bombs disappear from visual tracking without evidence of an explosion. Those bombs were victims of proximity bursts, the kind of subtle damage that did not produce a dramatic fireball, but still ended their flight. The Germans mistook silence for survival. They did not saw it was another form of defeat. From September 1st to September 7th, the Germans attempted multiple countermeasures. Higher altitude. SCR 584 tracked easily. Lower altitude. Guns adjusted. Mass salvo launches. The M9 predictor handled targets sequentially. Night launches. The radar was unaffected. Bad weather. Visibility did not matter. Every adaptation failed. The kill rate remained brutally high. Germany realized they were not fighting guns. They were fighting a system. By late August, the V-1 campaign had created 3 interconnected hells. 1. The hell of the gunners. They fought seconds, heat, exhaustion, responsibility. 2. The hell of Londoners. They waited in fear for the sound to stop. 3. The hell of the Germans. They watched their weapon fail in ways they could not explain. Each hell fed into the other. British gunners endured so Londoners could sleep a little longer. Londoners endured because they trusted the coastal guns. Germans endured their own confusion as they watched their vengeance weapon dismantled by an invisible force. The turning point was the tactical shift. The hell within was the human cost paid to reach it. By early September 1944, the German V-1 offensive was collapsing from within. Allied forces advancing across France after the breakout from Normandy approached the Pas-de-Calais region, the heart of the V-1 launch infrastructure. German units retreated in disorder, leaving behind damaged components, incomplete ramps, and empty supply dumps. But the collapse didn't begin with military retreat. It began weeks earlier, in the skies over the Channel. The soaring interception rates, the kind Germany's mathematicians considered impossible, had drained the campaign of meaning. A weapon once envisioned as a strategic equalizer had turned into an expensive, unreliable burden. Even as launch crews prepared each missile, there was a growing understanding within the German technical staff. Most of these V-1s would not survive the crossing. A Peenemünde engineer wrote on September 2nd, "We are launching metal across the water, and all we see returning are fragments landing in the surf." The morale of the V-1 program fractured the same way its missiles did, in midair. As the V-1 failure became undeniable, the German high command called for immediate countermeasures. Over several frantic meetings, engineers presented options with the quiet resignation of men who knew they were improvising against physics. 1. Change altitude profiles. Some V-1s were launched at 300 meters, others at 1,500, some at 2,700. Each altitude created a different arc across the Channel. Each altitude failed. The proximity fuse performed identically across the vertical envelope of British guns. 2. Adjust the launch angles. Low angles, high angles, angled trajectories. SCR 584 tracked them with the same degree of precision. 3. Launch in waves of 10, 20, 30 bombs. The Germans hoped saturation would overload British tracking, but the M9 predictor processed targets sequentially without confusion. 4. Conduct night launches. Radar ignored darkness. 5. Use bad weather as cover. Rain and fog had no effect. None of these adaptations dented the interception rate. The British defensive network did not behave like the old era of flak. It acted like a single unified weapon system. Every German solution died on contact with reality. By September 6th, the internal reports flowing into German command painted a grim picture. Observers noted that the British guns seemed to detonate shells on command at varying distances from the V-1. Never too early, never too late. Yet no British radar had the precision required to orchestrate such timing. The only logical conclusion was a fuse that detonated itself in relation to distance. But inside the German scientific community, this explanation was rejected before it was even considered. A proximity fuse violated everything they thought they understood about vacuum tubes, batteries, and the forces exerted on artillery shells. A German officer summarized the sentiment bluntly. If the British possess such a device, we are witnessing the future of warfare. But no one believed it. They were held captive by their own assumptions. Their textbooks said a proximity fuse was impossible, so the British could not possibly be using one. This intellectual blind spot sealed the fate of the V-1 campaign. Throughout the final week of August and the first week of September, London's Home Office noted a dramatic decline in V-1 impacts. Fewer bombs reached the city, fewer major fires, rapid declines in casualties. People still heard the pulse jet at night, but its approach lacked the same inevitability. The silence that followed the engine's cutoff often ended not with an explosion nearby, but with a distant detonation far beyond the city limits, or with no detonation at all. Londoners did not know why. They did not know that a barrier of thousands of tiny explosions was forming miles away over the channel. They did not know American fuses, British radar, and coastal artillery were saving the city each night. Most assumed Germany was weakening. Some believed the Luftwaffe had redirected resources. Others thought weather or terrain played a role. The truth remained locked behind layers of military secrecy. While the city exhaled, the men of the coastal batteries continued to sweat under the weight of their task. After every V-1 was destroyed, every gun crew resumed loading, cleaning, checking, preparing. For them, the night of August 28th, when 82% of incoming V-1s were destroyed, was just another shift. They did not know they had just created one of the war's most decisive defensive victories. On September 5, 1944, Allied artillery came within range of multiple V-1 sites. Launch ramps were abandoned mid-assembly. Workshops were burned. Ammunition stores were compromised or destroyed. Within 48 hours, German command issued the final order. Cease all ground-launched V-1 operations. Continue launches only from aircraft when possible. But air-launched V-1s were few. Their accuracy was worse. Their rate of fire was a fraction of ground sites, and their vulnerability to Allied fighters was absolute. The V-1 campaign was dead. VT fuses had killed it as surely as they killed the missiles themselves. In May 1945, after the surrender, American and British intelligence teams interrogated the engineers who had overseen the V-1 campaign. Oberst Max Wachtel admitted, "We suspected better radar, but we never imagined a shell that could decide when to explode." Other engineers were shown a captured proximity fuse. Their reactions bordered on disbelief. They examined miniature vacuum tubes that survived 20,000 grams, a glass ampule battery activated by shock, a thyrotron switch the size of a small finger, circuitry embedded in hardened plastic. One scientist whispered, "We are a decade behind this." For many German engineers, the realization stung deeper than every failed launch. They had not been defeated by pilots or by soldiers or by tactics. They had been defeated by industry, by mass production, by an idea they considered impossible. The humiliation was scientific as well as military. For an entire summer, British gun crews had fired secret ammunition without understanding its significance. After the war ended, the War Office conducted controlled debriefings. Men who had served on the diver belt gathered in barracks and lecture rooms. Officers dismantled an actual proximity fuse in front of them and explained how it had worked. One gunner wrote, "We thought we were just firing better shells. We never knew we were holding something that changed the whole war." Another said, "We saved London without knowing how." I'm not sure whether to be proud or ashamed that we didn't understand it. The secrecy that had protected the fuse had also concealed pride. Only after victory could these men understand the role they played. By the end of the offensive, 9,521 V-1s fired from ground sites. 2,515 reached London. 6,184 civilians killed. 17,981 injured. Without the proximity fuse in the diver belt, the death toll could have reached 30,000 to 40,000. General Pyle said, "No other wartime invention saved more civilian lives in such a short span." The V-1 campaign, intended to break British morale, ultimately strengthened it. When historians analyze the V-1 campaign, they often emphasize the weapon's terror or the tactical challenge it posed. But the most important lesson lies elsewhere. Germany pursued perfection, handcrafted rockets, advanced jets, exotic research. The United States pursued scale, millions of reliable components, thousands of workers, unified production. Germany sought the ideal weapon. America sought the effective weapon. The proximity fuse embodied this difference. 1. It was small rather than grand. 2. Practical rather than elegant. 3. Built in factories rather than laboratories. And because it could be mass-produced, it multiplied the power of every gun in Britain's arsenal. Germany fought a war of prototypes. America fought a war of systems. When those philosophies collided, victory belonged not to the most advanced weapon, but to the weapon that could be built by the millions and delivered anywhere. The V-1 campaign teaches that war in the modern age is decided in engineering offices, in assembly lines, in logistics hubs, in the industrial rhythm of a nation. The battlefield is only the final stage. The proximity fuse did not fade away after 1945. Its principles became the backbone of radar altimeters, air defense missiles, guided munitions, electronic fuse for modern artillery. Its legacy lives in every weapon that uses distance sensing technology. But its most profound legacy is something simpler. It proved that mass-producing a good idea can defeat a perfect idea. Germany handcrafted brilliance in small quantities. America built effectiveness in overwhelming numbers. On the day British guns destroyed 82% of incoming V-1s, warfare changed direction. The era of handcrafted wonder weapons ended. The era of industrial, integrated warfare began. And the Germans launching their missiles across the Channel never understood what killed them. They had done everything their science told them was right. Yet they were beaten by a miniature circuit encased in wax and plastic, built by factory workers who did not even know what they were making. Through tens of thousands of tiny explosions, London survived. And the war moved irrevocably toward a future defined not by individual genius, but by the collective power of free societies working together.